Hi, good evening, everyone. So this is our session 5, reviewing homework 3 and sorry, there's some echoes. So we're going to review homework 3 and we're going to review clustering. So if you are reviewing this lecture from a web session, this is the Wimba. So last time it did not work, maybe because I was trying to archive the session, plus trying to record, plus trying to run. So probably it was consuming a lot of memory. And I'm trying to get rid of the echo here, so bear with me. Okay. So maybe if you want next week, you can try to log on to Wimba. And the classroom is microarray, and you can see my name here, my phone number, and I'm sharing the desktop. So maybe it should work. I'm hoping. All right. So I just want to make sure that R works before I get more into this lecture. Just give me 1 second. It does take a lot of time, but okay, should work. Okay, so let me maximize the R screen. And let me go back to Wimba. Give me 1 second. Maybe just have a little bit of volume here. Okay, so let's review assignment 3. On assignment 3, what you're trying to do in essence, that you have a data set. Oh, sorry, the echo really bothers me. Sorry, guys. Wonder if there's a mute button somewhere. Okay. So we found this data from nextbio.com, so hopefully you guys can check out this website. It's a great repository to find a data set on microarray and etc. So we are going to use two methods today with the same data set. We're going to try to find differential expression using MALT-T-test, which is FWER, family-wise error rate type 1 control, and by Cygnus, which is SAM, which is the FDR or type 2 control. And our hope is we're going to find at least 25 genes that are differentially expressed by using these two methods and try to compare to see what commonality do we have, if any, between these two methods. You were everything that you needed other than the dataset that you're trying with for the SAM was uploaded under lecture 3 for this particular PDF file, and the Vignet for MALT-T-test.pdf should tell you how to do the MALT-T-test portion. In addition, I gave you the hints in the homework. So that was your data source, right? And these are the hints that I hoped helped you somewhat. And we're supposed to do some listing. So now let's jump into the solution of it. Okay. So this is assignment 3. You're practicing multiple test and SAM, two different methods. And I am running this under R version 2.8.0. As usual, the first thing that I do is try to find out where which directory you're working from. So in my case, it's different than you. I have a folder called R1. And in this folder, what I did is I went to the website that tells you in the assignment here for your data source, which is right over here, right? So once you got to that zip file, and then you are to unzip it, and you should see 16 cell files. So these are the 16 cell files I have exactly, and I put that in my R1 folder, and they're all named exactly as how I extracted, and they all end with a .cell file extraction. So that's the first step. All your cell files are under your R1 folder. Second step is you have to create a treat.txt. I think you're going to use AffyPack package to load your data and construct the expression set object. In order for you to do that, you need to create a treat.txt file. In that treat.txt file, just like the way we did the cough.desk.txt in my assignment 2, we're going to indicate for each of these cell files which condition they belong to. And how do you know which condition, which file belongs where? If you go to this URL, you should have a file called columns.txt that should tell you which cell file belongs to which condition. So let me show you the treat.txt file briefly. So this is the treat.txt. So in this cell file, the way I have done it, you could have done it many different ways. You could have separated by a space, you could have separated by a tab, semicolon, colon, comma, whatever of your choice. So in my scenario, I did it by semicolon. The first column is the ID of the cell file, so I have 16 of them. In the second column, I'm indicating what are the conditions of the diabetic, right? So in my scenario, my first 10 files are not diabetic, and my bottom 6 files are diabetic. And that's I also picked up from the text file that I showed you. So 10 non-diabetic and 6 diabetic. And we're going to do some differential expression between these two conditions. I am also giving you some note here, right? So when you are creating your treat.txt file, my column header is ID here. The column header here is diabetic. And you will find those exact notes here. A header as ID. It should match exactly. So whatever you're typing here for your cell files should match exactly what I had in my R1 folder for my cell files. That's the first check. Then I'm indicating under diabetic which 10 files were condition N and which 6 files were condition Y. And I have separated them by a semicolon, and you can do it any way you choose. So one thing interesting, as you will see as we practice, go through the solution, the chip type or CDF file, sorry, the Affy platform is actually not HGU95AV2, which I thought was the last homework that you did. In this scenario, it will be HU6800. So when you're calling annotation and etc., it should match to the Affy platform that you're using. Okay. In homework 2, unfortunately, some of you had some difficulty in getting to the correct packages and importing the library and etc. So as I again repeating, anytime you want to upload a bioconductor package, the first command should be the source so that you make a connection to the bioconductor website, and this is the script that will enable you to import the packages you need. So in my scenario, by default the Cygnus, Multitus, etc. package does not come. So you have to individually select those packages and import it. So if you don't have the Cygnus package, Multitus package, or the annotation package for the different platform HU6800, which you're analyzing this time, if you don't have those packages, then you would want to import that. So I'm not going to go through doing this because I already did import it. It's in my laptop. So if you don't have it, that's what you would have needed to do. So this is what I just did now. I loaded all the libraries that I need. I set my R to pointing to my R1 folder where my cell files are. So this is the pre-steps, right? So you have your cell file, you have a treat.txt telling which cell file belongs to which condition. You have imported all the library that are required for you to carry on with this assignment. Your R is pointing to the correct directory. Now it's time to do some analysis. Okay, so there are many ways to read and many different packages are available. You worked with simple AFI last time. This time we're working with AFI package. And AFI package is built on the BioBase package, where you had a good exercise, and I'm very impressed to see all of you did a very good job in having a fundamental understanding, how from a text file you can construct an expression set object, phenodata object, annotation object, annotated data frame, which is an object that leads you to the phenodata object. So your fundamental building blocks that are required, that's built out of some base R modules and classes, are pretty clear to you. So I'm very good to see how you did that on your homework 2 task 1. So no need to repeat those. So phenodata object, right, it's built out of the annotated data frame. So that's the function that's available. So in that function or the method, you can put the treat.txt, which will tell you which cell file belongs where. You want to read the header, and it's separated by semicolon. That's how I showed you earlier. So let's read the phenodata. Oops. So that's what happens when I am using the Wimba. I'm not seeing the file getting executed. So what I need to do, and that was the problem we ran into last time, I need to log out of Wimba. Let me close this. So let's exit. Okay, good. So it's on the records now. Wimba doesn't work, in case PolyID cares to look at it. So let's try to run it now. I'm hoping it'll work this time. Voila, it works, right? So now I'm reading. So any kind of memory intensive process that I want to run in R, you run into that when you do some high performance computing. You obviously are not going to do it from your laptop. You'll probably have dedicated Unix servers and etc. to do it, but given the limited resource pool I have in my laptop, and Wimba probably is built on a Java application, and if they are not doing the GC collection and memory collection optimized, so then it's a contention and R just gives up. So enough with Wimba, doesn't work. Good to see that. So now let's move on with our R program here. So verify, you read the phenodata. So this is an annotated data frame object. We know that. So let's look at it, how it looks, and you can use the pdata method to look at it. So it looks good, right? So you have your 16 cell files. The first 10 are your diabetic, non-diabetic, and the other 6 are your diabetic condition. So we are good there. Let's verify the class. I like to do that. You don't have to. So it's an annotated data frame type of class, right, which is the phenodata. Then we are good in reading up to the phenodata. Now you want to construct the assay data, okay, which is basically a matrix of your samples on the column and your probes on the rows. So you can use the read-AFI function for that. One thing that happens when you use the read-AFI, and I use function and method interchangeably, so pardon me, they're not the same thing, but I mean the same thing. Function always returns a value. Our method is something that does a job for you. So in this case, I should really say it's a method, but if sometimes as I'm speaking I incorrectly say it's a function, just be mindful of the difference and pardon when I say that. So let's use the read-AFI method. So if you don't use anything in the argument over here, so what it is going to do, any cell file and every cell file that you have on your working directory is going to read all of them. But you don't want that. You may have at a given time on your working directory many different cell files. It depends. But assuming you have many different cell files, you should only get the cell files that's available on your phenodata. So there's 16 of them. So if phenodata is an annotated data frame, so if you just get the row names, so you should get these 16 row names of the cell files itself. So that's the row name, remember? And diabetic is the column name, and these are the values. So if you do a row name of phenodata, then that will give you the cell files. So the argument inside the file names should be those cell files. And you can verify it, maybe perhaps just running this command. So if I do that, right? Okay, so now file names, if you look at file names itself, it should give you those 16 cell files that you have. Okay, so now let's read that. So we're reading the expression data. So as it's reading, the next step logically that you would do, and we will put all this together when we're doing our project, even though in the homework I may be targeting an individual piece or individual workflow, but in homework, sorry, in the project, you should try to connect it all together, which is, you start with your files, then you are going to construct your expression set and Phenodata object, then you're going to do a QC. That QC should show you the one that we did in homework 2, plus additionally some news plot or maybe some fit that you might want to do, FEPLM package. Then you're going to do some differential expression using either SAM or Cygnus or simple t-test. Then you're going to do some annotation. Then you're going to run some more topics on hypergeometric test and Go and maybe mapping to pathway. And I will make it very interesting for you, perhaps, if you, when you go into the project level, maybe you want to do some analysis across the experiments, right? And then you do a meta-analysis. That's what the students in last semester did, and that was great. So maybe something that you, if it interests you, you can do that, or if you want to do some different topic, we can also discuss. We are perhaps about a week or more behind than what we would have liked to, ideally, and unfortunately we're not there, so we need to catch up, and I need to start engaging on the discussion on project. But I just think that so far in the class you have only experienced how to read data and maybe do some differential expression. You're getting some exposure to the clustering, but you still haven't gone to the point of geometric test and Go. So you need to understand those. Then you also need to understand comparison between multiple time points, which is lemma, then meta-analysis, so you can connect the whole end-to-end picture. Then you can think about what project you want to invest on. So you just read your expression data. So let's just get the class of the expression data. So this is an AFI batch, so which is an expression set object. So in your expression set object, it consists of the assay data, it consists of the pheno data. Right now it doesn't have any annotation and etc. So whatever you constructed up until now is no different than what you did in task 1 of assignment 2 and part of the COVDES TST that you did in assignment 2 for task 2. I'm going to skip the QC, but I just want to say that it's a standard practice just right after you construct or before you construct your expression set object, just based on the raw data, you should see what's the quality of your cell files. So if you see that the quality of your cell files are not good, I would recommend don't proceed doing analysis. That's what you would do in real life, right? But even though I don't ask you in homework, try to be mindful. Good practice to do some QC. If we haven't done it for the homework, that's fine. But let's move on and focus on areas that we need to learn and that's new for us. So now that we have the expression set object, we have the different building blocks we need. Now the time comes to do the background correction, normalization, and summarization. So in this scenario, we're using RMA. Future homeworks, I might want to ask you to do GCRMA, or I might ask you to do Mass5, etc. Different algorithms. D-CHIPS is another one which you haven't done. So this one, let's just do it by RMA. So that should be simple. Same thing, use the just RMA method, just like you did the readFE method, and tell RMA which are the different file names that it should pick up, right, and do the processing to do the background correction, normalization, and summarization. So let it go ahead and do that. So normally, again, when you run it on your laptop or when I run it, it takes a much lesser time. But right now, it's again competing with the memory that it is doing while I record the session. So just so you guys know, why there is a delay, why it's taking time. But I have nothing but apologies to offer for this. But Wimba doesn't work at all. That's how it is. Okay. So now that we did the RMA expression data, so it's the same thing. So it's the expression set object, right? It just normalized, summarized, and background corrected it. So we still have 7,000 features and 16 samples. So this is a very old array they did the experiment on for 6800, right? But the new one, AG133A, I think has about 23,000 some features. So over here it has 7,000 features for the HU600 type object, sorry, annotation and AFI platform. So now that we have done the RMA, the next step that we want to do is we want to do some non-specific filtering. And we talked about in the last lectures what is a non-specific filtering by IQR and ROSDS. So I'm not going to get into that. You already are familiar with that. The criteria that we're going to establish here is anything that's greater than zero point 0.5. So first, let's write the filter function. And for the filter function to work, of course, you needed to import in your session the library gene filter, this one. So this one does all the work for you for non-specific filtering. So that's the function, and in this function, I'm going to use IKEA criteria of greater than 0.5. It could be greater than 0.8, right? But just something we asked in the homework. And pass that function into the filter fun as the parameter, which you're going to again call into the gene filter function. Right? So these are all functions. So you have one. You first define the function, put the parameter into the filter fun function. That function goes into the gene filter function. That's how it was authored into the Vignette. So now that we did that, what we need to do, so RMA expression data itself, right? If you look at the class of it, and this is a big jump, so you need to be patient in following that. RMA expression data itself is an expression set object. The expression set object consists of an asset data object, which is a matrix, and that matrix is only the values of your features and your samples and intensity. Then you have the phenodata object, which is the annotated data frame. So just working on RMA expression data, and if you want to just filter the probe sets and its intensity for IQR greater than 0.5, you are not concerned about the phenodata object and the annotation object that you have. You are only concerned about the matrix here, or the asset data, which contains the features and samples and its intensity value. So if what you want to do here, you want to cast the RMA expression data into an EXPRS, and if you do that, it actually constructs and just extracts the asset data or the matrix part of it from your expression set object. So bottom line is this one's class, if you look at it, was AFI batch, I thought, right? AFI expression set, which is same as AFI batch. So you don't want all components of the expression set. You only want the matrix component. And the way to do that is to cast it, right? For those, those who work with computers, you go from integer to float. So that's called the concept of casting. So you cast it, and then what it happens now, if you verify your class, it now becomes a matrix. So now, of that bigger piece, you only have the matrix piece. So out of that matrix, you can filter based on this function criteria. So that's what goes inside GenFilter, your RMA data, which is the matrix, and the FF is the criteria of what kind of functions you're using for IQR. You could have done a different ROSDS based function, which I'll show you in the SAM portion. You could have changed your filter in IQR criteria, etc. But I just wanted you to appreciate how you jumped from RMA data, from RMA expression data to RMA data. You basically went from expression set class to a matrix class or object, and you are doing this function on the matrix. So if you have seen this expression, try to understand why you did it, other than how it was hinted or you may have found in someone else's solution, or whatever it may be. So let's do that. We did the RMA filter and gene filters, so it should now reduce. Okay, so now we started with 7,000 features, right? So now that you have removed most of the features, do not have any variability or among them. So if they have a very low IQR, that means they don't have variability, right? So then it should now reduce based on you're only retaining those which has an IQR distance of greater than zero point 0.5. So anything less than that should be filtered out. So now if you do a sum of it, so or the dimension, you should know how many you have retained. So based on your filtered criteria, only 912 of them has selected. So that's a big jump, right? You started with 7,000 feature, now you went to 912. And as you go along doing other homeworks, that's all we're trying to do. We're starting from 20,000, doing a non-specific, going down to maybe, I don't know, 5,000. And from 5,000, we do a t-test, then you go down to like 2,000 or 200. And based on the 200, you apply some geometric test and Go annotation and pathway mapping. So end of the day, you may end up just finding 4, 5, or 10 features. Then you ask the question, does it make in a biological sense? Do I find these in any kind of literature? If it doesn't, throw away the analysis, do another one. You have to do several iterations of it. So it's a hunting. Many people are successful, some are unsuccessful, but that's pretty much the process here. Now that we have 920 of them, right, so what we have to do is our RMA data was the main matrix. So whenever you want to subset and go from a big matrix of 7,000 by 16 to now 912 by 16, you always have to reference the matrix itself. So if our RMA filtered itself, right, it's telling you what's true and what's false, right? So anything that 912, anything that falls within that will be true. Anything doesn't fall within that 912 will be false. So that the sum only gives you the sum of the true, which is 912. So now if you give in the RMA data matrix, and that's again, we talked about matrix subsetting. In the Boolean way, whatever is true, that should return. So from your RMA data, which is, if you look at the dimension of the RMA data, that should be 7,912. So if you subset it by RMA filtered, which is only true, it should now go down to 912. And you can verify that by the dimension. So this dimension of RMA data, which is your parent, that's what you started it, should be 7,912. Sorry, 7,129. And what you've subset that you just filtered over here from your parent matrix should be 912. So that's the difference, right? RMA data you got from your by casting from RMA expression data, and then further you subsetted the RMA data based on your filter criteria, so now you're down to 912. So for me, as long as you understand how you're making these transitions from one variable to the next, that is how you went from expression set object to a matrix by RMA filtered RMA data, and how you apply the filter condition RMA data to get RMA data filtered or RMA data selected, then you followed it. As long as you followed that concept, I'm confident that you're with us or with me. Okay, so now you're down to 912 and 16. So now you need to construct all the parameters that you need to run your MTXT, which is the multiple test. So you need your RMA data selected, which is the 912 features that you have based on the non-specific filtering. You need to tell the class label, meaning which of your 16 cell files which belongs to which condition. And then you're going to do a permutation of 2000. So fundamental theory behind this MT-MAX-T type of a procedure is you're reshuffling your class label and try to adjust your p-value, right, by doing the permutation. And all this theory we talked about in lecture 3. So the way you can then construct your class label is from your PD dollar. PD is the Phenodata object or annotated data frame. So we have two columns there. One is the file name, which is ID, and the other one is diabetic, which tells you 10 of them is non-diabetic and 6 of them is diabetic. So If you refer PD dollar $diabetic is equal to Y, so when it's equal, it should give 1. When it's not equal, it should give you 0. So you should get 10 zeros and 6 Ys, I think. But let's find out. So that's your CL. So now if you look at your CL, so so you verified, you got 10 zeros and you got 6 ones, so 10 non-diabetic and 6 diabetic. So now this the whole heart of what you're trying to do, or the engine for multi-test, lies in this empty.maxd function method, and you're going to give all the parameters here. So in the example, you may have seen the GOLAB data, right? ALL, AML. So all you have to do different is for your data set. So this is your RMA data. Those are your 10 class, 16 class label, and permutation is 2000 times. So let it run. Okay. So it ran, right? So REST-T. So now let's look at the first 10 rows of REST-T. So what it does, it shows you the REST-T object itself, and I think it's let's just find out the class. I think it is a data.frame or annotated data frame. I'm not sure, but we can always find out what it is based the way they implemented it. Data.frame, right? So this is a frame. So in this frame, you have the row names over here. So these are the different row names. So I'm just selecting the top 10, the first 10 here. These are actually sorted by the adjusted p-value. So this is the raw p-value that you started. So what is raw p-value? If you were to do a simple test statistics, remember test statistics is just a normal assumption is normal distribution, and then the whole industry and statistics is to take a step up and see if I permutate a bunch of things, and I'm going to adjust it. Am I still confident? So that's the adjusted p-values based on this empty.maxd method that you just did here. So this is already sorted by the adjusted p, so it's increasing. And see if your raw p, based on the assumption of test statistics where you had such a significance here, right? Such a low p-value. But once you adjusted it, it already went very high. So forget about finding something of p-value 0.05 adjusted. You're just not going to get it. So the question comes: do you want to stick to the adjustment because your power basically went down here because you just don't meet any criteria where you have a p-value of 0.05, or do you assume with a p-value of 0.05 for test statistics? My only recommendation is it doesn't matter. If you find by using a normal distribution and raw p-value that it is linking to a publication that's out there, so stick with that publication. If the fold change itself is giving you a good link, then rely on fold change. And if adjusted p-value is diverting you from a gold mine and misleading you just because we have some fancy way of doing that, take that with a grain of salt. Try all methods. Try adjusted p-value, try raw p-value, try simple fold change, and whichever leads you to the most meaningful connection to make sense biology-wise, that's your truth, not these fancy test statistics or adjustments that we're doing. But we need to know and understand how to do it, and that's the whole point of this course. So now you got that. So these are all the right data frame. You have your probes and you have your raw p-value and adjustments. So I'm going to take a 5 minutes break, and we're going to come to the rejection of the hypothesis based on our type 1 error rates, and we're going to do some ordering, and we're going to talk about how the next part of the engine gets created. So it's 6:35, and I should be back by 6:40. So as you're watching it later, you can also take a break. So I'll be right back. Yes, got back earlier. Okay, so let's understand the different columns. So this is the index. So this index is the position. So if you have 1 to 7,129 features, right? So this index tells you in the AFI, what row number it is. This is the name of that feature. Okay. Test statistics for each of these features one at a time. The raw p-value based on the assumption of student t-test or normal distribution. And this is the adjustment that got done based on empty.maxT method. Now we're going to do some ordering. We're going to first order it, right? This rest, which is a data frame, we're going to order it by the index that and store that into the ORD variable. So we did that, and these are all on your VigNet. So I'm just copying from there too, and you all did that in your homework also, at least the ones that I got a chance to look at. Then we're going to order the raw p. No, we're not going to order. Then we're going to get the raw p based on this order, which is this raw p value, and then we're going to also get the adjusted p value, which I'm calling the variable max t. So these are basically, this is already sorted based on the adjusted p-value, but for this function to run, or the method to run below, I'm just going to get the adjusted p-value based on the index order. So just because it's not ordered by index, so now the way they wrote this method, it has to be ordered by the index. So that's all I'm doing based on the VigNet that you had. So this is the core function, a method, right? So you're going to reject your hypothesis based on the criteria of type 1 error for alpha goes from 0 to 1. So what that means, it's the p-value, right? That's your criteria. So it could be adjusted p-value of 0.01, it could be 0.05. 1 is very high, but anyway, that's the maximum. So it could be anywhere. Your probability of or the p-value range can be between 0 to 1. So and then you're going to see, how many features are retained based on each of those criteria at 0.01 or at 0.02, right, or at 0.5. So that's the way it's done. It does it for the whole range. So you're going to do that by combining the raw p and the adjusted p, which is the same thing as max t. It has been ordered by the index, and your sequences, you're going to do it by 0.1. You could have also done it by 0.05, so that would give you 0, 0.5, 0.1, right? Some 0.15, then 0.2, etc. But the VigNet says, you just do it by 0.1, so you get 0, 0.1, 0.2, 0.3. So if you have a p-value of 0.05 or something, you might want to change it, how you are doing your sequencing here. But anyway, let's just run it. So we don't actually get a very good result. So what is showing us here that for a p-value between 0 is 0, so don't bother about that. So at p-value of 0.1 itself, which is much higher than the criteria I gave you in homework for 0.05, right? For 0.1 you don't get anything, or just 0, right? And but if you use the raw p-value, then you would have got 271. So that's when you want to ask the question, max t, I did all this adjustment, it's not giving me anything. So should I just go back and stick with the test statistics, assuming it's a normal distribution, and run with my analysis? You can obviously do that. And just so I didn't ask you in the homework, but I would do that if I were analyzing this data. So anything meaningful that I'm looking for, all it's showing me that it just simply doesn't work when I adjust it. The data set that I have, if I use the empty.maxT method, I'm just not going to get anything significant based on the criteria I gave you, 0.05. But just for the sake of carrying the homework, and I'm impressed to see some of you actually did that, we can just choose, I asked for 10 or 25 genes, so the most closest that I can get there is if I use greater than 0.6, I'll get 19. If you use 0.5 to show me 7 genes or 0.3 to show me 3 genes, that's fine. If you did not do anything beyond that, that's okay, but would have liked to seen something. This is a graduate class, expect you to do a little bit of critical thinking, not much, because I'm not capable of doing that much myself either. But at any rate, So if you use anything of between 0 to 0.5, it's not going to give you anything. So if I want to show you 19 features based on MaxT, I know ROPE gives me a lot. I will use the criteria of zero point 0.6. So that's what I'm going to do, which, right? So for this which, I'm going to reject. I'm going to take ROPE and MaxT together, and let's figure out, and I'm using comma 2 because that's the first column is the ROPE, which I'm not using. So which is, I'm just using the second column, so that means I'm only going to bother about the MaxT. So bottom line, this function is telling you based on your criteria of zero point 0.6, right, which you're going to get about 19 features. That's all it's going to do. So now if you look at your which, so it's going to be true for 19 cases, and for all the other cases you started with 900 and something, it's going to be false. So if you can look through it, you will see there will be only 19 of them. That's true. Now we need to extract. We need to extract out of that rest-t, so which is true, which again that was a data frame. So you're going to use the column 1, which is going to give you the index out of that data frame. So remember, this is the data frame. So you have first column, second column, third column, and fourth column. So what I want to do is, I know out of my 900 and some rows in this data frame, about 19 rows are true. So if I first extract it for column 1, I'm going to get the indexes. Then I'm going to go back to my original expression set and subset those 19 for the feature names. I think many students, including myself, when I was learning, I found it very difficult how you go back and forth between object and how you extract. But as you review some of the solution, I'm hoping you're paying attention, and I know you are, so it will be easier for you to make those transitions. That's why I assume one takes a class. Otherwise, you can always figure it out yourself, like I tried to do. Anyway, I digressed where we were. Okay, so if we do this now, right, based on the data frame on column 1, we're going to get some indexes. We're going to get 19 or so indexes, I thought, right? Or 0.6 should give me 19, right? So verify it. What happens is I do get those, right? So these are all the indexes that I got, 19 of them. And now what I need to do is I need to get to my original data set, and I know there is 19 of them. So now I need to get my feature names. And if I do that between these two steps over here, so having index is not good enough. What I need is the feature names, and in this probe set assay data, which gives me only the true. So out of those 900, only condition that means the true gets stored in probe set assay data. And if I do a row names on top of that, that should give me the feature names. So now, if you look at your probe sets, so you got your 19 feature names. So next thing you need to do, you need to connect those 19 feature names to using the annotation and get the gene name, and you're going to save it into an HTML report. And if you're not the biologist, you're going to call your biologist colleague and say, I have a great finding. I think we're going to get the Nobel Prize. Here are your 19 genes that's causing this diabetes, and let's make some $1 billion out of that. Maybe. So we have your probe sets, right? So these are your 19 probe sets. So now you already loaded the annotation 6800. So now you're going to get the gene symbols by using this particular method, and that was your ANA-Affy package had that. And then you're going to do this is from your textbook, and this is how you save it by using this method, AFTable ANN. This is your annotation that you are using, and that's all you needed to do. So that now is in the HTML format. Now you save the HTML with this particular file name, go back to your working directory and open it, and this is your probe set list based on the multi-test way I just showed you. Okay, so you can open it. It's hard for me to open these things, but that's how you saved it. So that concludes the work of the entire multi-test. So your SAM, which you're going to do on the same data set, It's going to be only easier. Now, be very careful when you talk about ALL dataset, and I know in the past it has also caused confusion. I'm only using the ALL dataset because that's how someone is giving us example in the textbook or in some of the vignette. So whatever I'm showing you in in the preparation or whatever you're reading on your textbook is done on ALL dataset. But when I'm asking you the homework, I'm not asking you to use ALL dataset. You have your 16 cell files. Those are what you're concerned with. You have no concern with ALL dataset. That's just for example. So when you're trying to import ALL dataset and you're stuck there, so my question is, why are you bothered for ALL dataset for your homework? That's just the dataset, right? Okay, so that concluded our multi-test method. So now let's review the SAM. Okay, so for SAM, we can also start with our RMA dataset. Okay, so if you look at the pipeline over here, it's going to be the same thing. You already read your data, so you have your expression data. You did RMA on it. So your starting data set of 7,112 or whatever features is stored here in RMA expression data. So I went down and did some non-specific filtering with IQR point 0.5, so RMA expression data now became RMA data. So in the homework, you also did, if you did that for the SAM, you probably also did the same thing. You started with RMA data here, which is the IQR based filtering. But just for the sake of showing it, instead of doing IQR in this solution, I'm going to do a non-specific filtering by using row SDS, so we can visualize that. In your homework, if you did by IQR, perfectly fine with me. But let's just do the non-specific filtering in another way, how your textbook shows it. So we start with the RMA expression data. Again, we have to cast it, so we only get the matrix that contains the actual data. You don't want to work with just like the way we did at the non-specific filtering. You don't want to work with your phenodata and others. That's part of those objects. So you're not concerned there. So we're casting it. So, oh, I'm so sorry. What did I do? I pasted everything. Sorry. Oh, now I wish I could kill it. Somehow when I copied it, got copied everything. Oh no. It's probably not going to be too bad. But anyway, this is how things get imported, right? Good to see it. I copied too much. I'm going to close out of this session maybe. Sorry guys. So it's going to go through all those codes that I selected above. I wish I could just cancel that session. Oh, okay. But I need to do it anyway again. So you get to see it. I'll just do what's relevant this time for Sam. Okay. So let's open the script. New session. So see. recording, I have this problem. So as your record recorded, you cannot open your folder. Just pure bad luck. So I'm gonna put it on the root folder here, or maybe I can open it. Okay. So try one more time. So let's try from the root folder, which is this, and it was assignment that. What was the name? Assignment 3. There. Sorry. Thought I had it. There it is. Open it. Okay. So what we're gonna do, very quick. Good to see it again anyway. So get the libraries. Okay. So let's get our directory set. All the cell files are there. Let's get the pheno data. Let's get the expression set object. So always do QC, right? Now we're going to do RMA on it. And what is RMA? Background correct, normalize, summarize. I think I'm going to ask one of you to do a presentation on to help me understand what is background correction mean in RMA. I think it would be good mini project if one of you in substituting your homework. So good thing to learn for us. So we'll just take this RMA expression data, okay, and then now I was just at the step of doing the non-specific filtering where I accidentally copied a bunch of stuff. So instead of showing and doing it by IQR, what I'm going to do is I'm going to show you row SDS, which is on your textbook. So the theory behind is if between features your variability is low, that means they don't have much of a standard deviation, then those you can get rid of. And those that has high standard deviation, so that means they would be more differentially expressed, you can retain it. So we'll do a plot and we'll establish a cutoff line. Anything that falls on the left of the plot with low standard deviation we're going to get rid of, and anything that falls on the right of the plot with high standard deviation that's going to pass the criteria of non-specific filtering. So I was with Sam, so let's go here, right? So this is where I was. So now we start with this RMA expression data, and then we're going to compare the standard deviations for between each of those features, and short it is according to your textbook that gives you the midpoint, and this is the value 0.18. So 0.18 is just like your IQR. You had a criteria of greater than zero point 0.5. So by row SDS, by using this function short, you actually get to that criteria. So I personally like row SDS more than I like IQR, and I really like to visualize it. So that tells me what I'm doing. So your 0.18, the criteria that you just got, is right about here, 0.18. So anything, and that gives you the frequency that's left of 0.18 is actually very low standard deviation, and these are the frequencies of those features which has a higher standard deviation. So greater than 0.18 means higher, 0.18 means is the threshold where 50% of them is probably on the left side, another 50% is on the right, roughly. So you establish this criteria. Now your subset are going to be only those that I'm circling here to the right. So this picture is worth of 1,000 words. So these are the subset that's going to be out of your 7,000. So roughly 4,000 should show up. So your RMA data selected then will be that's greater than SH. So that means to the right according to the picture I showed you. So let's do the dimension now to figure out how many came in. So about 4,600 features met the criteria where it's greater than your shorted value of 0.18. And now in your SAM, very similar to just what you did for your multi-test, three outputs, your data set or your matrix of your expression set object or asset data matrix that pass the non-specific criteria, your class labels. You already, I think I didn't calculate the class labels, so I have to redo it again here. So it should be 0 for 10 non-diabetic and 1 for 6 diabetic. So that's your class label, right? So CL. So same thing as you did at your MTXT, right? Your data set, your class label, how many times you want to permutate. Go back to SAM, you do the same thing. So here we come to the SAM and we do the same thing. Class label, random seed, and then we construct the model, sam.out. And our mt.maxd did not give a good result. I don't think so. SAM will also give you a good result when you're trying to adjust those p-values and whatnot. So let's look at sam.out, and picture will clarify this more for you. So these are the different delta or threshold criteria. In the last web session, I showed you, how you can adjust your boundary of delta and d bar when I worked with you on the ALL data set. So we told you there, what delta is. So I gave you a very high criteria of FDR of 0.015. I'm nowhere close here at 0.015. I think if I look at 0.015, maybe this one, 0.02, close to 0.015, I only get one feature that stands out. Maybe that one feature is significant, but for the sake of showing you a little more features and do some HTML output and whatnot, let's just choose a delta of maybe 0.5. So if I choose a delta of 0.5, I know 110 of my features are going to be called correctly, and 29 is false. So I'm going to get 29 false output, but that's okay. I can live with it, maybe. And I have 110 features that is called with a confidence criteria of 0.15 here. So it's a matter of optimization, picking the right delta. Same way you did on your mt.maxd method. You had p-values all the way from 0 to 1, right? So you had your unadjusted p-value, you have your adjusted p-value, you looked at different of them, see how many are getting called or not. So you took your pick based on your 0.05, which did not meet anything. I just showed you for the demonstration purpose by 0.6. Here 0.015 of FDR is also not meeting criteria, so for demonstration purpose I'm picking delta of 0.5, which is an FDR of 0.15, which is 15%, which is a very high call, right? But let's pick it and move on. So delta I'm picking 0.5 again. So if I pick delta 0.5, I should get 110 features and 29 false positive. So that's your delta 0.5, and let's do a plot now of this one. So if I do a plot, so your d bar again was the boundary here. So the more stringent you are with d, that you reduce this bar, you're gonna get less calls. So the more less it is So the less the width is, the more criteria or call that you're gonna get. And the wider it is, that D, then you're gonna get less. So at any way, so if this is so outside the boundary, we are actually seeing this many of 119 that are under overexpressed between diabetic and the other condition. You don't have any underexpression over there, and none of these are expressed. So whatever is beyond your boundary, it could have been on this boundary, or it could have been on that boundary. I don't know. I haven't looked whether this red is underexpressed and green is overexpressed, but I think that's the assumption. Okay, so you're gonna get 116 of them there. And so now, based on what I asked the last phase on the homework, you're gonna make a table out of that, and you're gonna put it into an HTML. So you're going to list that, and if you look at that over here, let's look at this one. So this should give you all the probe sets, right? So that probe set, just like the way you got in the multi-test, you're going to call the annotation, and you're going to just tabulate that result into an HTML file, and this is all the code, and all your HTML file gets saved, and that's the final line of your code. So what I would expect you do in the homework when I'm reviewing it, that you had reached up to this 2 point where your HTML files are there between SAM and RMA, and you're comparing to see what probe sets, or genes actually expressed in common between those two and what didn't. And there are a lot of things to think about. I mean, just reflect on what you just did. When you did the empty.maxT method, you really did not, the adjusted p-values were really high. When you did the SAM method, your FDR was really high, about 15%. So if you want to be very confident, but you're setting up this criteria as you're losing power. So then the question comes, do you not do those multi-test or SAM, or you do just rely on a simple t-test for your normal distribution, right? Then you get more features. And if you do get more features, then subsequently in next few lectures, you're going to learn how to connect those features to a pathway or to a Go annotation. And once you do that, and if it's making, again, I cannot overemphasize the word biological sense, then you have hit the gold mine. If it doesn't, then you can do a lot of fancy analysis, but it's just not useful. So that concludes the review of assignment 3. I'm going to upload that, and I'm going to try to review and grade your assignment this weekend. Should you have any question on assignment 3, feel free to reach out to me. And assignment 2, I hope everybody got a chance to look at it. I think I sort of lost gear when I was reviewing the assignment 2, and I may not have said few things correctly, but I think in the homework solution that I uploaded, and I don't know where I uploaded that, you should be able to review the volcano plot. So I haven't had any questions, so if you reviewed the solution for assignment, so volcano, let me see if I can open it. So this is the volcano plot that it should show up. So I think what we had was about 20 features that showed up, and you're supposed to print it like that. So when you take something on minus log p scale, so what happens, the low p values becomes a higher values, and that become here. So it makes sense, right? Because what is happening, and they were all overexpressed. There was no underexpression or negative fold change. So there was all positive fold change between the two groups of GSM file that you analyze. So what is showing you here at the end of the day, that you have sort of a high fold change and low p-value, and these are your overexpressed. So the volcano plot is the full FC versus fold change. The ideal condition you want to go is a very high fold change and very low p-value. So that's a very good one. And then maybe there is a way for you on this plot, other than just plotting it, also just kind of annotate the exact probe sets that you have. So if you can produce such an output and have this discussion on your presentation to say, this is how the overall landscape looked like, this is how the fold change were, p-values were, these regions seem significant, these are the genes that I'm outputting, this is the pathway that's mapping, and that would be a good tool set for you to have, on your future should you do this kind of work. So I think when I was doing the homework, it was plotting this way, and I just didn't do something correctly. And I also made some clarification on if you look at the notes of the homework solution I gave, the group by false, that's only, it should be only true when you're doing a replicate. But in our homework, you did not have any replicate. Each cell file belonged to its own condition. So the group by false, group by should have been false. So, but anyway, I think I corrected that on the solution that I posted and compare it. It was a little difficult in a way that how you were going from expression set to a data frame and you're extracting the t value, p value. So all you have to think about it when you think about this homework, you have to get the p values for all of your expressions or all of your cell files. You have to get the full change for all of your cell files, features in your cell files. So that's the overall entire. Then you run the test statistics based on the simple AFI pairwise filter, and you get about 20 or so that meets the criteria of p-value greater than 0.05. Those then you plot over here. So that's the difference. So everything versus what's differentially expressed, and those that are differentially expressed exactly showing the plot where they are. And something nice would be if one of you do that, show me what's the name of these features, right? Okay, so that's homework 2. Nobody asked me any question, so you guys are following it. And that's the SAM, and we did the multi-test. Now, time to move on to clustering. And I apologize, you're already in the middle of your homework, and I wanted to do this last time, but I think it took much more time, and I was in a training. So my apologies again. I haven't been able to keep up with the course in a manner that I would like to, but hopefully we can catch up. So we're done with this solution. So I will post it. So let's clear everything, clear console, and let's just start the clustering. So 7:08. So maybe we can wrap it up in next 40 minutes to complete today's session. Okay. So clustering. If you want to do the theory for clustering, and it's in your lecture 4 or lecture 5, I don't remember which folder it is, but you want to read, and irrespective of folder, you can go to ePoly and see all the files I have uploaded. So don't get bogged down to see what is in what folder. And if it's confusing, you ask me. But you can go to your Blackboard and see all the 200 or 300 whatever files I have uploaded. So read cluster.pdf and distance.pdf. So if you read these two files, that should give you the fundamental that's behind clustering. But in the course, we try to focus more on doing it hands-on through R. So I think I saved the cluster file here. Let me see. Okay. So now, for clustering, there are few concepts that you have to understand. And if some of you are going to Tom Girk's lab and following those exercises, you probably already have figured out. But if not, I will try to help you a little more from the point of view that I understand it. In clustering, it's very important to understand for each of your probe sets, when do you need to, you have a matrix, right? So row-wise, you have your features and column-wise samples. You need to understand when to transpose that matrix, meaning rows becomes columns and columns become rows. So a lot of people have confusion understanding that. You need to understand what do you mean by centering and what do I mean by scaling. You have to center and scale your data. So for any kind of machine learning that you want to do, the pre-processing, just like the way you did the normalization for your microarray data. So after the normalization step, you want to feed your data set to any kind of machine learning algorithm to do, let's say, clustering or classification. You have to center and scale the data. So for each column, the mean is 0 and standard deviation is 1. So you just assume you force those columns to be normally distributed. And the technique you do that is called centering and scaling. Then you feed it to your algorithm of hierarchical clustering or support vector machine or neural network. It's a whole course on it. I took it from ePoly, probably the best course I've taken from Poly. So if you can, take it. Um, so let's understand what's the concept of centering and scaling. So the way I will do that is I'm just going to create a very simple data set from 1 to 35, and I'm going to name the rows as probe sets and the columns as samples. And it's not going to be a normally distributed data. It's just from 1 to 35. So just look at the data set. So let me create it first. So that's your X. And let me increase the console maybe a little bit. It's very hard to speak to myself, but I'm trying hard. I can do that. Already did that for an hour and a half. Okay. Oops, sorry. So this is your matrix, right? So on the row wise you have the probe sets, and on the columns you have your samples, and I just made a value from 1 to 35. I did not use a normal distribution. So it's going to look funky when I scale it and center it. So what do I mean by center is take each of your column here, right? So the midpoint for each of these columns for sample 1 is 3, for sample 4 is 18, for sample 5 is 23, etc. That's how it applies. The formula for center is you take each of these values and you subtract it from the center. So this will be minus 2 because 1 minus 3 is minus 2. This will be minus 1, 0. This will be plus 1, and this will be plus 2. So that's centering. So you take the center or median, and each value is subtracted from the median. And it's also in the note, which I'll upload. And when you use the scale function in R, and you can actually do a help, when your scale is equal to false, it's actually doing the centering. I don't know, it's kind of weird how it's done. When the scale is equal to true, it does scaling and centering. When scale equals to false, it only does the centering. So you started with your X. So now if you look at your centered X, so what it did, so it subtracted 1 from 3. So that's just what I said, minus 2 minus 1, and 1 and 2 here, right? Because 4 minus 3 is 1, 5 minus 3 is 2. So now this each columns are centered. So meaning the center is 0 here. So that's all you did. Now you're going to do scaling, so your mean also becomes 0. Right now your median is 0. So you're going to now change the values on your probe, so your mean becomes 0. So the way you do your scaling is you take each value of the centered, which is minus 2, and you divide that by the standard deviation of the entire column. So over here, if I were to scale it, it will be minus 2 divided by the standard deviation of the entire column. So this particular first cell that I have, which is minus 2, it should be minus 2 divided by standard deviation of collection of the original values, which is 1, 2, 3, 4, 5. Right? Should give you minus 1.269. So that's the formula for scaling. So you take your centered value divided by the standard deviation of your original data set. So if I now use the scale on it, scale X, you should expect the first column, first cell, row's value minus 2 to become minus 1.269. And let's verify this. So if I now look at scale.x, right, it's minus 1.269, 2649, and you can validate that for all of them. So that's now it's centered and it's scaled. Okay. Now let's talk about the transpose. Why do you need to transpose scale? You right now you actually did the scaling by column wise, but it doesn't make any sense. Why doesn't it make any sense to do a scaling column wise here? Because these values of probe set 1 across the sample between this and this is not comparable. This could be a gene that's very highly expressed. That could be a gene that's very low expressed. So as far as this identity of this particular gene is concerned, if you jump around from one probe to next probe across a sample, that's not comparable. What's comparable is the identity itself. So this particular gene itself is expressed with minus 1.26 at sample 1, minus 1.26 sample 2. And the way it's coming this way, because I use from 1 to 35, so they're all appearing the same value. If you use a normally distributed data with some high and some lows and something in the middle, you're not going to get that, and we'll see that later. But just assume they're different. So you want to actually compare or scale values for the same probe sets across the samples. Because if you go this way, then you're jumping from one probe to next probe, and that doesn't make sense. You want to do for the single probe's value across the sample. And the only way you can do that is if you transpose it, that means flip it. So this row over here should become a column. And that's the concept of transpose. So your original X is this, right? So you have 1, 2, 3, 4, 5. But 2 is for probe 2 and 3 is for probe 3. So under sample, under probe 1, I want to say 1, 6, 11, 16, 31, all of that. So if I do that now, if I transpose this, and so all you have to do is T of X. X is your matrix. T is the method that transposes the matrix. So now if I look at my transpose dot X, right? So now you have your row names become column names, and your column names becomes row name. So now these values 1 through 31, which is 1 through 31, belongs only to probe 1, and now you want to make this probe 1's value centered and scaled. So I'm really hoping you made the mental jump of what is center scaling and what is transpose. You can always do it following some guidelines and books, but your only reason you're taking this class so you can understand why you're doing certain things, or I can help you rather understand to my limited capability of what's happening. Okay, so that's the concept of transposing. So now all we're going to do is we're going to first just center it. So scale is false is not, so I've started with this one. So if I look at my centered transport X, right? So this was the median value 16, so that becomes 0. So 1 minus 16 is minus 15. So you have that. So you can make this transition from here to there, what happened with center. And then now you can do the scale, and the scale would be just the scale of, then before you scale, what you want to do is you want to take your probes sets, right? So you already have your probe set, so you can actually do your scale on your transport.x. So your original X that you have, right, is 1, 2, 3, 4. So you want to transpose it. So your probes becomes columns and sample becomes rows. So that's my transpose here, and you want to scale on top of that. And if you do that, so if you specifically say scale equals to false, that just shows you the center. So that's what I showed you. When you don't give this argument, the scale function actually scales first, centers it, right? Then scales it, and transpose made that probes over there. So it's not very easy for me to speak to this. I tried my best, but I'm sure when you go through that and practice yourself, you can follow it. Think about scaling. First, you transpose it, then you use the scale function, which centers and scales it. So that's all there to it. Then, now that it's scaled and centered and everything, now you want to again bring it back to the original format of how it is. So then again retranspose it. So that's what is happening here. Now you retranspose it. So now your Y scale values, now back to what the probes were, back to where the samples were. So in the middle you did this shuffling, right, to transpose, align the probe, center scale. Now you bring it back. Now if you look at its standard deviation and scaling, in this case, since I did not use a normal distribution, you're not going to get a mean of 1. So it's going to be mean 0, standard deviation 0. Normally for a normal distribution data, I think the mean would be 0 and standard deviation would be 1. Because I used continuous value from 1 to 35, I ended up with mean and standard deviation both 0. So my end of the day matrix that I am going to use to cluster, right, and use for any machine learning algorithm is this. Now clustering is simply going to be, you're going to take a probe, and between these two samples you're going to compare the distance. So if this two has a similar distance, they're going to be more close to together for this probe set. Between this one and this one is a high distance, then this is going to be less related. So that's the whole concept of clustering, which I'm coming below. But so far all I wanted to cover is center, scale, transpose, retranspose. So you want to make sure when you get to your homework, you know you're doing it because of the reason what I showed you here. Okay, so now let's do the same thing with a normally distributed data. I'm moving on to a different example here. I use 1 to 35. I'm just creating another data set that's normally distributed, and I'm going to show you the concept of clustering. So let's look at Y here. So I have some samples, 5 samples, and I have some probes here, and these are all the normally distributed data that I got. Now what I'm going to do is I'm going to transpose it, right? Because that's what I just talked about. Your probes has to go to column and samples has to come to row. Then I will use the scale function. What that will do is it will center and scale it. Then I'm going to retranspose it back to how my Y originally is, back into probes and samples. So I spoke 20 minutes, right, for you to describe this. Think about it for a moment. It took me 20 minutes to describe to you what Y, Ty scale T, Y scaled is. And that's the effort I tried to make in this class. Okay, so now your Y scale should be again back same. You have your probes, you have your samples, but then now if you verify, all of their mean would be 0 and standard deviation would be 1. So it scales. It's ready for clustering. It's ready for comparison of distances. So understand distance. So I'm not going to go through it because we have 20 minutes left, but I highly recommend you study the distance.pdf and cluster.pdf. So distance, very simply, you can think of your geometry days of Euclidean distance. You have a point x1 and x2. So the distance between these two is, I forgot, it's x1 minus x2 whole square root over 2, something like that. Or you can do a Manhattan distance, which is just simply the absolute value of x minus y. So you can use simple geometric Euclidean. So all you're trying to do is between 2 points, right? So you have a sample here, and you have a sample there. So let's say this is a treatment condition, and this is drug-treated condition, and there is a feature here, or a gene. So you're going to simply, based on the numeric values that you're getting, you're going to subtract and get the distance. So there are many ways to get the distance between these 2 points. You can distance by Euclidean, you can distance by Manhattan, you can do distance by correlation, Pearson, and etc. So let's walk through all those examples. So we're going to use, so verify that your Y scale that you have here, your standard deviation should be 1, roughly, yeah, so this is 1. And your mean should be roughly 0 or close to 0. Or mean is 1, sorry. Your mean is 1 and your standard deviation is 1. So that's what you get for the way this normally distributed data is generated. So in my scenario, now that I have my Y, I should have used actually Y scaled here before I feed it into, but I incorrectly used Y. But I can still carry on explaining you the concept. So assume this Y is scale. So for now, for us to use this distance, we're going to use the Euclidean, which is just simple geometry. It's going to subtract between 2 points, take square root, and divide it by number of points. So that's first you define your distance function. So that's what it did now. So you have your probes between probe 1. So it took all the samples into consideration. Now it's just comparing what's the distance between sample to sample. So the 2 ways you will do this distance, you will want to see how close the samples are related, which is column wise, and then you're going to do how close the features itself are related, which is row wise. So between probe 1 and probe 2, the distance is 3, and between